Hey there, science fans! Have you ever looked around and wondered how the buildings you see every day came to be? That's the work of civil engineers. These amazing people use science and math to design and build the structures that make up our world. From towering skyscrapers to sturdy bridges, civil engineers shape our cities and connect us to each other. Civil engineering is all about using our knowledge to solve problems and improve people's lives. Think about the roads we travel on, the clean water we drink, and the safe homes we live in. All of these things are possible because of civil engineers. Civil engineering is a field that combines creativity with technical skills. It's about taking an idea and turning it into a real functioning structure that benefits society. And guess what? The foundation of it all lies in the fascinating worlds of math and physics. Now let's talk about math. Math is like a secret code that helps engineers design structures that are both safe and strong. Just like you need to measure ingredients carefully when baking a cake, civil engineers use math to calculate the exact dimensions and amounts of materials needed for their projects. Imagine building a skyscraper. You wouldn't want it to be too tall and wobbly, right? That's where math comes in. Engineers use equations to figure out how much weight a structure can hold, how strong the foundation needs to be, and even how wind might affect the building's stability. Math also helps engineers create detailed plans and blueprints. These blueprints are like instructions for the construction team, showing them exactly how everything should be built. It's like putting together a giant puzzle, but instead of pieces, you're using beams, columns, and concrete. But wait, there's more. Math is like the blueprint, but physics is the engine that makes everything work. Physics helps us understand how forces like gravity and pressure affect structures. It's like a game of balance, where engineers need to make sure the forces pushing down on a building are evenly distributed. Ever wondered how bridges can be so long and strong? Physics explains that. Engineers use their knowledge of forces and materials to create arches, beams, and cables that can support incredible weights. And then, there's energy. Physics helps engineers design buildings that are energy efficient. By understanding how heat and light move through different materials, they can create structures that stay cool in the summer and warm in the winter, saving energy and protecting our planet. Let's take a trip back in time. Did you know that even ancient civilizations used math and physics to build incredible structures? Take the Egyptian pyramids, for example. These massive tombs were built with incredible precision, using ramps, levers, and a whole lot of geometry. The ancient Romans were masters of engineering too. They built aqueducts to transport water over long distances, using arches and gravity to keep the water flowing. They also built roads and bridges that are still standing today, a testament to their understanding of materials and forces. Fast forward to today, and we have towering skyscrapers that seem to touch the clouds. These modern marvels are built using advanced materials like steel and reinforced concrete, and engineers rely on sophisticated computer programs to design them. But even with all our technology, the basic principles of math and physics remain the same. Section 5: Bridges, spanning gaps with math and physics. Bridges are some of the most impressive examples of civil engineering. They connect people and places, allowing us to cross rivers, valleys, and even oceans. But have you ever stopped to think about how they actually work? There are many different types of bridges, each with its own unique design. Beam bridges use strong horizontal beams supported by piers. Suspension bridges, like the Golden Gate, use massive cables strung between towers. The cables are under tension, while the towers are under compression. Arch bridges, like the Sydney Harbour Bridge, use a curved structure to transfer the load. Math and physics play a crucial role in bridge design and construction. Section 6: Tunnels, conquering mountains with math and physics. Tunnels are an incredible example of how civil engineers use math and physics to overcome natural obstacles. Whether it's tunneling through mountains or digging underground, tunnels require a deep understanding of the forces at play. Building a tunnel starts with careful geological surveys. Engineers need to understand the type of soil and rock, and any groundwater hazards. Once conditions are understood, engineers design the tunnel and choose the construction method. Common methods include drilling and blasting, tunnel boring machines, and cut and cover tunneling. Tunnels are a testament to human ingenuity and our ability to conquer challenging environments. Section 7: Dams harnessing water with math and physics. Dams are massive structures that hold back water, creating reservoirs that provide us with drinking water, irrigation for crops, and hydroelectric power. Building a dam is a monumental task that requires a deep understanding of physics and math. Engineers must consider the force of the water pushing against the dam, which increases with depth. This force is known as hydrostatic pressure, and it's one of the most significant forces that a dam must withstand. The shape of a dam is crucial to its stability. Most dams are thicker at the bottom and narrower at the top. This design helps to distribute the water pressure more evenly, with the greatest pressure at the base where the dam is strongest. Engineers also carefully consider the materials used to build a dam. Concrete is a common material because it is strong under compression. The concrete is often reinforced with steel bars to increase its tensile strength, allowing it to withstand the outward pressure from the water. Building a dam is a delicate balance of forces and materials. It's a testament to the power of civil engineering to harness natural resources for the benefit of humanity. Section 8. Roads and Highways. Connecting the world with math and physics. Roads and highways are the arteries of our transportation system, connecting cities and towns and allowing people and goods to move freely. While they may seem relatively simple compared to bridges or tunnels, the design and construction of roads and highways still rely heavily on math and physics. Engineers consider factors like traffic volume, vehicle weight, and speed limits when designing roads. They use mathematical formulas to calculate the appropriate thickness and composition of the pavement, ensuring that it can withstand the constant stress of vehicles driving over it. The slope of the road is another crucial consideration. Engineers use trigonometry to calculate the appropriate angles for hills and curves, ensuring that vehicles can safely navigate the road at the designated speed limit. Drainage is also essential to prevent water from pooling on the road surface, which can lead to hydroplaning and accidents. Next time you're driving down the road, take a moment to appreciate the engineering marvel beneath your wheels. It's a testament to the power of math and physics to connect our world and keep us moving. Section 9. Airports taking flight with math and physics. Airports are gateways to the world, connecting us across continents and oceans. From the runways to the terminals, every aspect of airport design is a testament to the power of math and physics. Runway length is critical for safe takeoffs and landings. Engineers use physics equations to calculate the distance an aircraft needs to reach a certain speed for takeoff. Considering factors like aircraft weight, wind conditions, and air density, the layout of taxiways and gates is carefully planned to ensure the efficient movement of aircraft on the ground. Engineers use computer simulations to model traffic flow and optimize the airport's layout for maximum efficiency. Airport terminals are designed to handle large volumes of passengers and luggage. Engineers consider factors like crowd flow, queuing times, and baggage handling systems to create a smooth and efficient passenger experience. Airports are a symphony of engineering, with every element working together to ensure the safe and efficient movement of people and aircraft. And underpinning it all are the fundamental principles of math and physics. Section 10. Math and Physics Essential Tools for a Sustainable Future. As our world faces challenges like climate change and resource depletion, the role of civil engineering in creating a sustainable future has never been more critical. And at the heart of this challenge are the powerful tools of math and physics. Engineers are using these tools to design buildings that are energy efficient, reducing our reliance on fossil fuels. They are developing new materials with a lower environmental impact and exploring innovative construction methods that minimize waste and pollution. Math and physics are essential for understanding and mitigating the impacts of climate change. Engineers use these tools to model sea level rise, design coastal defenses, and develop strategies for adapting to a changing climate. The future of civil engineering is about creating a built environment that is in harmony with the natural world. And math and physics will continue to be the essential tools for achieving this goal. Section 11. Appreciating the math and physics around us. So there you have it, science fans. Math and physics are everywhere in our built environment. From the bridges we cross to the buildings we inhabit, these fundamental principles shape the world around us. Next time you step outside, take a moment to appreciate the engineering marvels that surround you. Look for the arches, beams, and cables that hold up our structures. Think about the forces at play and the careful calculations that went into their design. Math and physics might seem like subjects confined to textbooks, but they are so much more than that. They are the tools that allow us to build a better world, one structure at a time. Stay curious, keep exploring, and never stop asking, how does that work?